Hey guys. Okay, so today we are going to start working towards the mean problems. We spent 3 lessons on proportions. The first one, if you remember, I introduced proportions to you. Just what does it mean to have a difference of two proportions from two populations? We used sample evidence to support findings about the difference of the two populations. So we did that with confidence intervals, and then we did that with hypothesis tests. We are going to mimic that feeling and start working on means problems. So no more proportions. We're not given counts this time out of our total sample. This time we are doing numerical data. So we are doing a collection of values. So we have a measured number from each person in our sample that we are gathering and then analyzing and calculating the mean from. Remember, proportion problems are counts. Those are not measured data. Those are categorical data situations where we have just how many out of the total. So if you look at this problem already, you should be able to see we have scores for Form A and Form B. We have a list of numbers. Numerical data gives you either the list of numbers or they will have to tell you the mean and standard deviation ahead of time. So if you look at the notations, the X bars on the paper should give you that clue as to, oh, hey, I'm now working with numerical data. Anytime you start a problem where it's not sorted for you, you don't know what type you have, that's the first thought that should go into your head. Is it a proportion or is it a mean? Is my data counted or is it measured? Is it categorical? Is it numerical? Okay, so work through those questions and make sure you know what you're dealing with before you begin. Otherwise, you're not going to know whether to choose proportions or means in your work shown or in your calculator tests, and you're going to need to know what type you've got. Okay, so here we go. We are going to start to this first lesson of chapter 23 of just what does it mean to have a difference of two means. Okay, so we're not starting in with intervals or tests yet. We're just going to look at the comparison of two populations and what that distribution would look like, just like we did with proportion problems. So our situation, last year, East Kentwood High School had 30 students take the AP exam, statistics exam. We were informed later that the College Board gave 2 forms of the exam. Yes, they actually do that, which were randomly assigned to the students. Here are the results. So we've got Form A and Form B, and those were the scores from each of the forms. It's asking you to find the mean of both of them individually. So you have 2 options to find the mean. To set us up for confidence intervals and hypothesis testing, I think what I'd like you to do is to go back and practice putting these into lists and then calculating the means and standard deviations and such from your one variable stats, because that's really where we're going with this, and might as well practice it where we have a less intimidating lesson. Okay, so let's make Form A list 1, and let's make Form B list 2 in our calculators. And then in your calculator, remember that when you are trying to enter information into a list, push your stats button. Not second, it's not the list, it's just the stats button. And then you choose to edit, which is the very first one, number 1. And then after you do that, it'll show you all your lists. Go up and push clear when you're in L1. It'll clear out the data for you. If you push delete, it's okay. If you meet with me or ask me, I can show you how to reinsert it if you accidentally deleted one of your columns, or you could just use list 2 or list 3 or list 4. It doesn't matter which lists you use as long as you know where that your data is. Okay, so let's enter all of these numbers into our lists. I'm doing that right now. Hopefully you are too. Okay, I got my first 15 and my second 15 is going in right now. Okay, So once you have all your data entered into your lists, then you are going to want to exit back out of there. So you could push quit, or you could to exit out of there, it's the second mode button, or just go back to your calculator function, however you choose to do it on yours. I don't know what you're doing. And then now we need to do our calculations. So we're going to the stats button. If you want to quit by just pushing the stat button again, you could do it that way. So many options. And then this time you're going to scroll over to calculate, and you are going to choose one variable stats, and then you have to tell it which list you want to use. So remember, your list is going to be list 1. There is no frequency list. Remember, frequency list is how often each of those numbers got used. They each just got used once. There's no list of frequencies. So we don't put anything there, just leave it blank. Push calculate. And the first thing that pops up in the information of the statistics is the mean. So for form A, which was X bar A, we have a mean of 4.2. Do the same thing for list B. You should end up getting a mean of 4.0. Okay, the other information we're not using right now, but the nice thing is by entering it into the lists of your calculator, if later on in the lesson we want the standard deviation or something else, we can just go back, run one variable stats, and grab it. We don't have to keep re-entering all those numbers. That's why lists are so helpful. They save your numbers for you, calculate the mean, but then you can do any other thing over and over again. Your lists don't disappear. Okay, so what is exactly the difference in the means? Try to ignore the orange part right now. I was doing some previous setup for the lesson, so ignore the orange. The difference in the means is going to be 4.2 minus 4.0, which is 0.2. So what that actually implies is that according to this sample, it appears that students scored higher on form A than form B because the difference in their means is a positive difference. So this would indicate that form A would probably have been easier. Now, again, this is only one sample of data, and we don't know at this point whether or not form A or form B is actually easier. So we're going to investigate what it means to actually be truly random. So assume the forms are the same difficulty. If that's the case, Doug scored a 5 on form A. He will also score a 5 on form B. In other words, it doesn't matter which form he took. So if that's the case, you should be able to take all 30 numbers and shuffle them up into 2 new piles of 15 each. So that's exactly what I did. I went to random.org, like we've done before, and I typed in all 30 numbers, and then I hit randomize my list. And the first 15 I made form A, the second 15 numbers I made form B. And you can do this as many times as you want. So if you want to do it yourself and play with it and see what differences and means you come up with, you can. This is just random.org under the list randomizer. I used it before in one of our previous lessons, so hopefully it looks familiar to you. Okay, so that's what I did. And the orange numbers that I wrote down for A and B was that first round I did of 2 sets of 15 numbers, purely random. So I'm going to write down here that this is truly random. So there's no difference in the 2 forms of their difficulties. If that's the case, then what I found was that my mean of that first data set was 3.93 for form A, 4.13 for form B, and it gave me a difference of negative 0.2. So, okay, that's fine. If I wanted to do this over and over again, I could use this little graph below to start collecting data on when there truly isn't a difference between the two forms. So I could start building a distribution. If we were in the class, I would have each of you guys do this on your own. I wish you were, so that way we could collect the data and then have 30 different dots to look at. Right now, I just did it twice, but I'll put in some extra dots to kind of show you what it would be. So that first one I did was at negative 0.2. And I actually did it a second time. I showed my work over on the side over there. I did it a second time and I got positive 0.2 here. I can keep doing this over and over again, okay? Odds are I will probably get dots to form a sort of a normal curve. What we're looking for is our difference in the mean scores in comparison to what Kentwood was claiming. So if you remember, Kentwood was claiming that they had a difference in difficulty of 0.2, and is it surprising? Well, here's a difficulty of 0.2 where A was the easier test, that's the positive version, and where B was the easier test, that's the negative version. They didn't actually really specify which form was easier or harder, so we have to just go with both. This is a not equal to situation. We don't know which form is easier or harder. We just know that they're different. So if we're just trying to see the difference, then we would count all of these dots on both directions to calculate our p-value. It's going to be those number of green dots out of however many dots we had total. Okay. Now, if you are looking at mine, obviously you could see that I only did it twice and both my dots are outside of that in that p-value zone of 2 out of 2. So right now my p-value is 100%, which is pretty funny because we're looking for a p-value that's less than 5%. Yeah, not exactly statistically significant right now. If we kept running this, then I would expect to have like some dots in here, maybe here, a few gathering, maybe a couple out here, something like this. But even if we used that as our estimate, we'd have 1, 2, 3, 4, 5, 6, 7 dots out of, let's see, 1, 2, 3, 4, 5, out of 13. That's still a really big p-value. 7 out of 13 in terms of a decimal is 0.54. So no, this is not surprising because according to what we're looking at, assuming, let's define our p-value here, assuming both forms are the same difficulty. We would have a 0.54 probability of getting this difference that Kentwood saw of 0.2 or higher purely by chance. There's a 54% chance of just getting this because it was random. So no, we're not convinced that Form A and Form B are different in their difficulty levels. For this, according to what we don't have anything statistically significant to use. Okay, so this result is not surprising. We can answer question number 4 at this point. More than 5% because our p-value is larger than a significance level of 5% by a lot. We do not have convincing evidence that the true difference in the proportions showed one form was harder than the other. Oh, I said proportions. I'm so sorry. You could tell I'm used to doing those ones. The true difference in means. Okay, so that's the reality. We do not have evidence. Remember, we're trying to check to see, is one form more difficult? We do not have evidence that one form is more difficult than the other. That's the gist of it. So what we're doing right here is we're setting you up to understand how the wording for those conclusions are going to be when we change to mean problems. As you can tell, it sounds very similar to the proportion problems. It's just you have to say the true difference in means, which is funny because I didn't. But remember to say means when you do yours on these problems. Be sure you're continuing with the language of the situation. Okay, so let's look at kind of the big ideas of this lesson. It's not anything major. This lesson was just meant to introduce you to mean problems again, because we just spent 3 lessons on proportions, and mean problems feel a little bit different. Okay. So big ideas on this one. Remember, if we're talking about a distribution of means, then if we were trying to describe the distribution, we are talking about the shape, center, and the spread. And our sampling distribution is going to be for our mean of 1 versus mean of 2. So sampling distribution would be x bar 1 minus x bar 2. Remember, your sampling distribution is based on your sample values that you found. So that's why I used x bars. Okay, the actual notation and stuff. Let's go through if we were to just have to describe this distribution. So shape. Remember that you're looking for the hopefully approximately normal model. You have a couple ways to verify that. Either the population was normal, unimodal, and symmetric. Or if you don't have any information about the population's shape, because that's a guarantee. If the population is normal, your sampling distribution is safe. You don't have to check anything. If you don't know, then you either have to verify by the central limit theorem that you have a sample size that is larger than 30. Remember, that is called the central limit theorem. If you have a sample size bigger than 30, you don't need to check anything. You don't need to look at any pictures. You're done. Voila. If you don't have any information about the population or your sample size is small, then you have to go look at the shape of the sample. And if that's the case, you're looking for no strong skewness, no outliers with unimodal. So same idea as before. Unimodal and symmetric with no outliers. So again, the shape of our distribution can be verified in many ways. Usually we just stick to that one. That's kind of our basic way. But if we don't have a sample size of 30, then we resort to this, and we have to draw it. I'm just reminding you that that is part of the picture showing the work. If you don't know that you have a big enough sample size, then you better draw what that distribution looks like on your piece of paper. When we get to confidence intervals and hypothesis tests, don't worry, I'll be sure that we do that so that you have a reminder of what to do. Okay, the shape is there. The center, the mean of our sampling distribution, is going to be the mean of the population's difference. which in this case, we don't know what that true population difference is, but if we were going to write it in symbols, oops, I put 1 and 1, sorry. That's how we would write it. Okay, and then the spread, this hopefully is starting to feel familiar with, since we just did the difference of proportions. Still differences, we got doubling up of everything. We just have to switch over to our standard deviation symbols. Now for the spread, our standard deviation of the sampling distribution, x bar 1 minus x bar 2, is a little bit different than just doing 2 separate standard deviations put together, because a single sample sampling distribution is just your standard deviation over the square root of n. But when we have to combine them together, remember, it's like combining random variables. And I actually went through this on one of our recent previous lessons. We have to square those standard deviations over their sample size before we can take the square root, because we have to combine them together when there is no negative sign involved. So when we're doing the differences, remember, it's actually adding the negative standard deviation of 2, but when we square it, it'll become positive. Okay, so we have gone through that idea already a couple times, but I know I didn't write it down here. I said it out loud. Rewind this if you need to hear that again to make sure you're understanding why the standard deviation looks like that. Again, these formulas should be found on your formula page. It does not need to be memorized. Know where they're at so you can use them on the AP exam. And all those notes you were doing in my class on your formula page, yay, you're at home. You get to use any notes and anything you want to. So mark up that formula page with anything and everything that will help you as you're going through and taking that exam, okay? Okay, so time for the check for understanding. Now that we've gone over everything, pause the video, try to take a minute to see if you can walk through these problems on your own. This one problem. Walk through the problem on your own, and then unpause me and play it to hear how I did it and see if yours matches up with mine. Okay, I'll see you in a minute. So for the check for understanding problem, the heights of young men follow a normal distribution with a mean of 69.3. Notice they used M and W for men and women instead of 1 and 2. Remember, I said in proportion problems, you can do it either way. Sometimes letters are helpful because we don't have to clarify what's what. That was the mean inches. Standard deviation was 2.8 inches. The heights of young women follow a normal distribution with a mean of 64.5 inches and a standard deviation of 2.5 inches. Supposedly, we select independent simple random samples of 16 young men and 9 young women and calculate the sample heights, the mean of the men and the mean of the women. What is the shape of the sampling distribution and why? Okay, so let's start in with what we know. The shape, I'm going to color coordinate these for you. The shape of our sampling distribution is going to be approximately normal. And I didn't annotate the problem because I'm going to do that now as we answer these questions. The why is because up in the beginning, it said that the men had a normal distribution and the women's population had a normal distribution. So the reason why is because both the men and the women populations are normal. Okay. Next part, find the mean of the sampling distribution, x bar m minus x bar w. So we take the mean of the populations and we use those to calculate the mean of the sampling distribution. Okay, back to what we know about sampling distributions. The mean of the sampling distribution should be the same as the mean of the population. That's the big idea. There's no adjustments made. They should match up because you're talking about the center of your graph. I really do hope if you've put together a sampling distribution and you've calculated the means of all these samples and then put those into one big distribution, that it should really well match up with your population. Okay, so let's use a notation. The big thing right now isn't understanding, because we've done this for a while. It's going to be notation. So the mean of our sampling distribution of the difference between, oops, I wrote 1 and 2. I'm used to that. Men and women are going to be the same as the mean difference in their populations, which is mu of men minus mu of W. And then we can use our numbers. So that's what the symbols look like in terms of numbers. We've got 69.3 minus 64.5. That difference is going to be 4.8. So the mean of our sampling distribution is going to be 4.8. Okay? And up here, the numbers I used, I have boxed in green. Those were the mean of our populations individually. Subtract them, you'll find their mean, the difference of their means, and then that should match your sampling distribution. Okay, last up, calculate and interpret the standard deviation of the sampling distribution. So standard deviation does have to be adjusted. It doesn't match the populations because samples are not the same as population variability. Okay, so we have to adjust it for our sample size. Remember our notation first. So the standard deviation of our sampling distribution of men minus women. I put Y. All these letters are throwing me off. Looks like this. And in terms of what the formula looks like, we wrote it up above in red, but I'll write it again here. It's going to be the population of men's standard deviation squared divided by the sample size of men, plus the population of women's standard deviation squared divided by the sample size of the women. Okay, so I'm trying to keep my notation to match what they did in the problem. Sample size of men was 2.8. Sample size of women was 2.5. 16 young men, 9 young women. So that's all the information you need. We are going to do the square root of 2.8 squared over 16. Notice the 2.8 is the only part that's squared. The 16 is not. Be careful on that when you enter it in your calculator. And then we're adding to it the 2.5 squared over the 9. Once you enter that into your calculator, you should get a standard deviation of 1.088. So if we were to create a picture of this distribution, I'm going to draw it off to the side for you so you understand what we just found. Our mean would be at 4.8, and if it's approximately normal, it should span out to about 3 standard deviations above and below the mean. So this should be 5.8. We'll make that 1.1, so we'll call it 5.9. That would be 7.0 and 8.1 if we added the 1.1 on each time. And then obviously same thing going the other direction. If they asked you to draw what this distribution would look like, -2 and then -3 standard deviations, subtract off the 1.1, so you'll get 3.7, 2.6, and then 1.5. Okay, so I wanted to show this to you because I want to remind you that as we go through and run confidence intervals, usually, because that's the lesson that's going to come up next, usually we look at this 95% interval, which goes between 2 and -2 standard deviations around. And then if we're looking at hypothesis testing, so this is for a confidence interval. If we're looking at hypothesis testing, we are looking for that teeny tiny area under the curve that is outside of our z-scores. And we're looking at that percent as our p-value. Okay, So if you have two tails like this, it would be a two-tailed test and not equal to sign for your hypothesis test alternative. And if you only had one of those sides, then you would have a single-tailed either left or right, depending on whether it was a greater than or less than. Okay, so I just wanted to draw it to kind of help start you off thinking of how we're going to use this for our intervals and for our hypothesis tests with p-values. Next lesson up is going to be the intervals, and I will see you then. Good luck on this practice for Khan Academy.